Yeah, warm welcome to this seminar. Um, looking at interest of the people in different subject matters, we will have a seminars going for webinars going forward as well. Touching different topics surrounding to this particular technology. Myself, Kushal Kesrod, as Sekimi has already introduced me. I take care of technical activities at TechVibe System Private Limited. We have a we are a small, humble company having good technical background as well as a lot of customers base, having almost 60 years of cumulative experience, handling very niche technologies. So, before we begin today's topic, I would just take you a few more minutes and talk about what TechWive System Private Limited do. So, what do? We do a production process optimization under which any processes in the manufacturing or a production, like whether it is QC, QA, or tool design, fixture design, and things like that, can be utilized in order to maximize efficiency and quality in production workflow. That's one area in which we work. Another area, tolerance stack-up analysis, ensuring precision and assembly process that we handle. Any part level tolerances, how do they come when it comes to an assembly? So is what tolerance stack-up analysis, under tolerance stack-up analysis we do. We have engineering services related to this particular technology, as well as we have a products also to offer. And another division under which we basically handle engineering and process simulation technologies in the areas of structural analysis, multi-body dynamics, CFD. In fact, some of the manufacturing simulation as well. One of that we are basically going to talk about today, sheet metal forming simulation. But we have welding simulation, then 3D printing, metal 3D printing simulation, and so on. So with that, these are the partners through which we get all these high-end technologies which we talk about. 3DCS essentially handles geometric dimensioning and tolerances and helps us getting assembly variation. We will be in a position to do the tolerance optimization, part level tolerance optimization. We can not only optimize the individual tolerance, but we can also optimize datums, locator schemes, and so on, so that we are able to minimize repair, rework, and rejection. That's the motive. 3DCS is the, I believe, only tolerance stack-up analysis tool which can in fact handle some of the thermal and mechanical loads on variation, not only variation due to tolerances, but variation due to clamping force or welding distortion or any other thermal loads because of which variation is happening. Hexagon, pretty much very well known for its high-end simulation solution in the area of structure, multi-body dynamics, CFD, fatigue, and as I said, some of the manufacturing process simulation like welding, forging, and additive manufacturing. Hexagon also has got a lot of production-related technologies, hardware and software both, CMM, scanners to do QC, and QC and a QA related software as well to integrate the complete process. Sorry. Dynaform is the third company that we represent, and we are going to talk a little more detail about what Dynaform do and how this particular software basically helps us in different areas like farmability, nesting, any cost estimation that is done at RFQ level, streamline optimization, till even die structure analysis as well. Scrap shredding is something which is unique in this particular domain. That also can be handled eventually with the new uh, modules. Anyway, so about Dynaform, which is sheet metal simulation and a die simulation software. So Dynaform 7.2 is the latest version, which basically for driving efficiency, profitability for manufacturing sheet metal forming manufacturing people and an industry. So these are some of the esteemed customers which are basically using Dynaform for their day-to-day die design, simulation, nesting, cost estimation. Couple of Indian OEMs also you can see Maruti Suzuki, um, and G-Stam is another Indian company which uses LG electronics, but it's a growing further, and it is being used not only by OEMs, tier one suppliers, but it is being used even by white good manufacturers and line builders like ThyssenKrupp and so on. So with this, I would just want to emphasize what one should basically look at when they basically get into sheet metal forming simulation solution. So what is that one can expect? Formability study, whether I'm able to form the given component or not. Ultimate aim is to, I mean, one of the major aim is to improve, yield or material utilization, and ultimately achieving the cost optimization. Accurate trimline is one of the very, very important. Otherwise, you may have to rework things later once the component is formed. So that we want to avoid. Die face design to get desired stretch, least wrinkles, or I would say no tears. That is where die face design is very, very important. Conventionally, people do that in CAD software itself with their whatever intuition or a design experience they have. But Dynaform can actually help you validating whatever die face design you do over here itself, after analyzing whether it is providing me appropriate stretch or not. Progressive die design is something where farming simulation is very, very important, because any induced thing that are basically happening in previous stages, you should be able to um, take it to the next stage. That is where it becomes very, very critical and important. Another criticality, comes as a definitely critical is a spring back analysis, a spring back and a spring back compensation for tool designers. Um, though you may probably design your die appropriately, perfect after extracting the part surfaces, but because of the spring back behavior or spring back phenomena in the component, you know you you don't get final product what you needed. So that is where spring back analysis and spring back compensation comes in. Okay, I mean, all the um, sheet metal forming dies that you do in forming simulation, die is considered as a rigid. So you're not considering any flexibility in the die. But ultimately, die also is made up of some structure, isn't it? So depending on its size and the loads which are actually coming onto it, it may compliant, it may show some flexibility. So that flexibility can cause you two things. One is inaccurate farming in itself. Second, life of the die, because if you want to actually carry out farming strokes, maybe thousands or lakhs or millions, depends. You should ensure that the die basically will be used for that particular uh, part of its life. So that is where die structure analysis comes in, line transfer simulation, scrap shading. Some of the topics I have actually kept for a future reference, because in one go we'll not be in a position to cover all of them. So we have different modules in Dynaform. One of that is blank size engineering, under which you are able to simply do unfolding. But unlike what you do in CAD, CAD basically unfolds just simply same area as what your part is. But here it is also considered, the stretching and all those, even at this particular stage. So unfold sheet metal geometry, quick formability, you can use it for obviously nesting, whether it is uh, multiple outline, or a single outline, multiple part, and single part, or even assembly level nesting also can be done, and you can as well do cost estimation. Pretty much quick in doing that. Then comes a die face design. After you have your part, you should be in a position to properly define the addendum before you reach to a die face, and your die face also should basically help you, bringing a properly formed component. In addition to that, you will be in a position to also define um, beads in the die face design area so that you get appropriate stretch, things like that. Formability simulation, where deep drawing and a line die, progressive die, spring back and a spring back compensation, all these, draw bit optimization, all these you will be in a position to do it at this stage. That is what formability simulation is. While it uses our own internal solver called SIGFORM, it can as well use LSDyna as a solver, external solver. So Dynaform, being a very nice user friendly pre and a post processing environment, it makes use of both the solvers like SIGFORM and LSDyna. Blank trimline development is another module in which you can optimize your trimline with the multiple iterations, um, so that you don't have to, rework your model after final draw. And there is a module for tube bending and forming. One, because it's a hexa corner, one of the corner was very important, which is DSI, die structure integrity, which is not shown here. But then tube bending and a forming, again, it uses LSDyna as a solver, uh, only LSDyna as a solver, I would say. With this, we can actually touch to a basic and a very important module called blank size engineering. It, as I said earlier as well, it uses it helps you to unfold the geometry, early check of formability, and material cost estimation by carrying out nesting operation. It it can actually do a single part and asymmetric multi-part blanking and a nesting solution. BSC also uses you know welded blanks, tailored welded blanks, and patchwork blanks. It basically helps us material relation analysis for blanking, nesting, and strip concepts. So I'll directly take you to software and show you an example so that you understand it better. When we open Dynaform, this is how it looks like. It's pretty simple. The project that we basically see is to manage complete data in a single directory. Then you have a processes like VSE, DFD, FS. You can import the geometry. Let me just create a new project quickly. Um, DF 9000, some numbers. You can mention a directory in which everything will fall in the single directory under the same name of the project that we have given. And there are different applications that, Dynaform basically does. So we are selecting blank size engineering and going ahead. Under blank site engineering, again, you are able to do outline formabilities, nesting multiple outlines, unfold. assembly BSc, and so on. Um, but we're again going ahead with a few basic things, right? Here, if you look at some of the icons which are not used at this stage, are basically disabled automatically. So user don't get confused. Okay. Then obviously geometry is something that we need to import in to start with. Then we have all the views. I mean, how do you basically want to see geometry shaded or a wireframe, meshing shaded or wireframe though, and the views, standard views like top view, front view, if you want to rotate, all sort of things. Yeah, shaded edges, shaded, and here also meshing. How do you want to basically see? Then some of the very common utilities like angle measurement, length measurement, and so on. And finally, which is disabled, see, finally the result C. So I want to just see unfold by importing the geometry, a simple component, sheet metal component that we can just import and quickly do unfolding and see that. Yeah. Here, when it is doing unfolding, it anyway needs mesh. So please keep this in mind. It's unlike CAD tools that it does. So you can refine meshing if you want at this stage. Uh, Tipping, it automatically takes if you choose auto. Um, Farming needs really a appropriate tipping. Here it's okay even if you're not mentioning that. Then then there is a material library which you can have an access to. If I click on material library, you have US material, Europe standard material, China, Japan, and you can as well define user defined material library as well. So I'm selecting one of that, which basically provides me hardening curve, yield surface. I mean, how the within the surface, how the sheet is basically getting stretched, and finally the forming line curve, limit curve. Say, okay, I've chosen that, and I can say unfold. Yeah, you can see unfolded component and a final component also. I'll just switch on the final one so that you are able to see only unfolded one. At this stage also, I will be able to see the formability report. So let me just quickly show you what different options you will be able to see under formability. So you can see thickness, variation, thinning in the terms of percentage, minimum major principal strain, FLD, and so on. So you can actually choose what you want, which format do you want, and apply so that you get report, quick report. So formability, you can see how percentage thinning is basically shown here in a different orientation. Most likely it remains in the range of I think below 5% only. Um, and you as well see major principal strand and so on. We have only chosen two part. Otherwise it would have been little more detailed report. Okay. So Let me let me show you next, which is nesting. Most important. So for whatever blank that we see here, if it has to take out of the coil, you can create nesting that you want. There are different types of orientation that you have in series. Parameters for coil also can be mentioned. What is the width? Yeah, you can do it in pairing, you can do it in mirror, even the based on draw also you will be in a position to uh, take the size. And blank fitting, different options you have. Automatically it chooses some particular orientation. You can see what is the area utilization it has in a weight. Complete detail it shows you. But in case you want to make any changes manually, you will be in a position to change its rotation orientation. However, it basically shows you real-time weight change and area change. So automatic, pretty much it gives optimum. You can say, okay, that fitting is okay for me, and let's create the nesting. So even before creating between both the blanks, what are the distances that you want to keep, bridge span and anyways, if I'm actually cutting them with a laser cut, 2 mm is more than sufficient for me so that I'm able to utilize better material. So it shows me highest utilization is 55.304 with the multiple iterations that you have. You can choose which iteration you want to go ahead with. You can see each and every iteration by clicking on it, how those orientations are happening. Now, on top of that, there are some of the functionalities at the bottom. That is, you can actually further click and adjust things manually as well within this particular iteration. So rotations, translation, and all those you will be able to let me just, yeah, this is how it is. It could be too much, but then you will be in a position to make some changes here as well. Okay, so I don't want to, I simply want to cancel that. Don't want to make any changes manually and generate report. Now when we click on report, there are, like again, what type of report you want, whether it is um, Excel or something, you choose that, and then production volume you can mention. Here the rate INR per kg, I can let me mention. I am not sure if it is correct, but then 80 rupees is what I'm mentioning. Material handling or something cost is 2 rupees per kg, and consumable is 1 rupee. And I'm just saying up, I'm just applying that. Okay, so it is generating a report in Excel format is what we have chosen. Um, and it will show me what cost it will take to make 1,000 components, because we are actually giving production volume as 1,000. Coil length was anyway considered earlier. It provides me date on which the report is generated, what was the file name, units that were used, material type that was basically chosen, thickness of the material, breeze gap, and all those. It gives me all inputs, before. And then on after nesting layout below, you see, yeah, these are the cost inputs that we have given, and below you see what is the pitch distance between both the blanks, then the total width that it requires, what is the percentage material utilization, product area, and even what scrap volume you are going to get, value, not only volume, because we have already given rate for the scrap is 25 rupees. So total scrap value is this much. Nice detailed report, given. So let us just come back again. Now this particular opening, if it is large enough, we are able to accommodate some small component in it. So small components blank also can be taken into it. So there is something called part in the hole. So that cutout is going anyway waste. So before we do that cutout, I want to basically take out some small blank out of that. Okay, so define small outline. You can define it over here, or you can import that. All these are the small, I mean, holes, small and a big holes. But these bigger holes is where I want to utilize by putting some small blank. So I'm just simply, creating it uh, manually, not importing any geometry. I'm just creating that rectangular you can create, let's say, two different rectangles, small, so that, you're able to take, or maybe a single large one. Okay, I'm just, for example, I'm defining one small rectangle and say, okay, apply, say, okay. Now in the nesting, you are able to see some small blanks are actually taken out. You can see the dark borders inside the, and now the utilization it shows is 60%. Before it was showing 55%, right? And if you extract report, obviously, the most of the things will remain same. We're not any making any changes here in terms of USD and all those, because of time constraints. So it's simply going continue and taking that. So here we will only focus on what is the percentage utilization improved from 55 to 60% is what it is showing us. Yeah. 1 minute. Okay. So let me take you to a little one advanced example, um, which basically um, within the BSE, um, it instead of importing here simple one, we're going in a part and seeing advanced option of that. Under advanced option, we have something called tailor welded blank. Okay, so blank, in fact, it's the name itself shows, there could be two different materials. There could be change in the thickness, change in material, and so on. It is basically a tailor welded blank. Okay, so we're going to choose. Um, yeah, let me select the surfaces which are falling in blank one, including that, and under blank two, I want to select the remaining surfaces. All right, so let me select. There are many good selection method here. I mean, it's very user friendly. Eventually, one can learn it to handle better way. So yeah, both the blanks you can actually define. Let me define different thicknesses. 1.2. Sorry, it's 1.2. Then 1.3. Let me choose material and another material here maybe. So there may be different material, different thickness, or same material, different thickness, or something like that. Okay. So now you can see under nesting, you can, I mean, anyways, we can do unfolding first. But under nesting, you see, tailor weld blank one, blank two. So there are two blanks. Yeah. This is first blank and second blank. So uh, let's do a nesting for under progressive for second only, which is little complex compared to first one. So this is how it will basically show you. And let me just select another option, mirror nesting. This time, uh, rest, blank outline, and all those will keep same. Yeah, I'm just keeping it as it is. Then carrier distribution, I want to keep that as a center. And when I'm selecting that, you can see in above figure A, B, I mean B, um, D, E, all those I am actually making 10 mm only. Sorry, B I think is a between two, this thing. Let me just increase that so that there is a sufficient gap between mirror blanks that we use. And optimization can be done based on maximum utilization or minimum cost. Ultimately, both the same. Here, it could be little different also because it is tailor made, having different material, different thicknesses. So uh, you can mention those cost of the coils and all those. I'm saying just apply. You are able to see the utilization here, 68 point some percentage in the topmost. Again, same thing. We have already seen manual translation or orientation change. Um, yeah, I think I can skip this. We have already seen that. And then breezing. I mean, when we are actually having mirror type of blanks, if you basically want to carry them together in progressive, you can base connect them. That is what is called bridging. So rectangular type of bridging, I want to place somewhere between this, and only one side you are creating bridge, automatically second side it is taking because you have already used mirror. Again, there is another functionality, called insert the hole there, somewhere, so that for positioning, you may probably use this locator hole. So I'm just mentioning 5 radius hole to be placed in this area. This area anyways is going to go in scrap, but in progressive die you will be in a position to place your blanks properly. Okay. So this is how detailed, all functionality it has, and then you can generate generate report. Again, after, I mean, yeah, obviously before generating the report, you can mention what are the rates, so that it gives you complete estimation. Yeah. Here it shows you all inputs that you have given, what was the production volume, what is the rate that you have given, and finally, uh, mm, related to blank. So, the single blank, it is basically costing you 200 rupees, and total cost of production is around 10 lakh, I think. Yeah, 10 lakh. Scrap is around 1,95,000. So that's how it is. Okay, so in fact, one more option here we have is assembly uh, nesting. So you can have a 10 component, 20 component of the sheet metal components in single assembly, and it can actually help you estimating cost for all the components. Another module that we're going to see is die phase design. To This is mainly conventionally done in software, but as I said, it is basically done by an experience of the designer and intuition. But advantage of creating addendum and die phase here is you will be in a position to check them quickly over here itself. You can as well add beads, their parameters quickly, and even the capacity and all this. Okay. So quick and easy die phase design enables more accurate, more robust estimation process, and it increases process reliability, efficiency, and cost reduction. So die phase preparation is one of the thing that this particular module is used for. Binder creation, obviously beyond the die phase, the flat areas, not exactly flat, but yeah, flatter areas, and addendum creation. Addendum is basically a between die phase and a part. So in between part. Okay. Uh, let's just have a look at the options that we have for handling this particular thing. I'm sorry, 1 minute. So DFD is the name of the project we'll create. fender is the part for which we are basically going to define die face. So this is the part for which we are basically going to design die face. And here there are going to be two operation. Uh, There'll be flanging also. So firstly, we have to define the material that it uses, and then mm, yeah, here it's a flanging. So you're just choosing surfaces which are pretty much flat, and then adjacent to that, it automatically selects the flange area, and you can see how it can differentiate that. Smart enough to understand. Then when it comes to um, yeah, tipping obviously makes difference how its addendum and orientation is going to come, but we can directly go to body fill. There is automatic way of filling it so that you major areas where undercut and all can be filled. Um, it automatically extracts the boundary around, and it uses curve based on the options that you give. 300 is the radius that you have given. But some places, if it is not acceptable, you can probably do even manual also by right clicking that. And I'm just creating manual curve in this zone particularly. Yeah, and this is the binder area, just taken a larger than it requires, and these are all control curves that we need to define along and across the length and breadth of the component. This is just to ensure that giving different control to a different segments. So ultimately, our ultimate aim is to smoothly define how from, I mean, above the tipping plane and below tipping plane um, zone, how the curves should be. So we are actually trying to make curves very smooth, and you can see there are curve 1, 2, 3, 4 that we have actually defined, and we are simply treating their roundness, and transition, I would say. So that is most important. So once that is defined, we can yeah, you're able to mention its actual location where it has to be, so that it makes it smooth. And once it is done, you can accept that. Now, this is addendum design, where you are actually giving different dimensions. Uh, so that material flows properly, right? So you are essentially defining the bar and a row, um, radius of the bar and so on at different locations. So once these parameters are defined, you can see this is how the addendum is created. Now, binder area, I want to, make it limited. It's not necessary that it should have all the complete outside region. That much area is not needed. So we're just defining that this is going to be kind of nearby blank to us. After trimming, you will be able to define the optimum blank size. Yeah. So uh, I mean, you are able to animate and see how forming is going to take place. Ultimate aim is to see whether I'm getting a proper output. You can actually, whenever you submit the problem, this is the window it will appear, job submission window where your jobs can be in queue, in progress. You will be able to see that, and once it is completed, you can actually right click and see the results out of that. And when we come back to Dynaform again to see results, um, it depends on what you have requested for. The results that you have requested, this first one is basically um, FLD. Yeah, and FLD basically provides you a lot of insights in terms of, what is the whether insufficient stretch the component has. So insufficient stretch is there in the component. There is severe wrinkles, but anyway, it is appearing outside of the component, and there are safe areas here, and there are some wrinkle tendencies on the component itself. So our aim is to make at least component area should be properly stretched and safe, so that it will not have cracks, or it will not have even wrinkles also. That's our aim. So now what could be the changes that tool designer would want to make? So he may probably introduce beads in these areas, binder areas, so that the material flow properly happens, right? So that is what comes next. So permeability simulation, under which you will be able to see how best my permeability is happening. Again, stretch, wrinkles, and all those you'll be able to see, review the results, diagnose them. What is thinning coming? What is the spring back? How can you compensate and all those? So this is another very important module. What we have actually now project is a farming simulation, and we're going to use basically sheet farming as an option here. You can choose the different folders so that all the results related to farming goes there, and sheet farming is the option that we have chosen. Here, the moment you select farming, you have crash farming, you have single action with pad, double action, uh, all these operations. You can simply drop them down. This is basically trimming, flanging. So let me take trimming first and then flanging. However, in case you take different sequence, you will be able to change the sequence of operation from here by uh, pulling down something that you want to change. So this is my sequence of operation that I have chosen. So this is just outline that you have defined. The content is not there yet. So operation 10, operation 20, operation 30. Okay. Now we can import in geometry that are required. One beautiful thing here is, whether you have a geometry in step formats, IGS format, or a different combination of formats that you have in the folder, you will be able to simply import all of them together. All right. And once it is done, because they are in a different layers, you can see curves fall in a different place, surfaces are in different place, and so on. Okay, you can start defining things one by one in the model. So this is just geometry environment we are in. So you are able to see everything. But once we are out of this location, um, once we exit this location and go back to operations, you don't see anything here, because once we select those geometries in this environment, they can get converted into mesh. So I want to define outline of the blank. So define outline. You can simply add it. I mean, you can as well create, but we already have it actually. So just selecting it from the screen and say okay, done. And there is something which remains undefined. That's the reason blank is basically so material selection. And once it is done, it automatically turns black. So in short, all basic things are defined. And you can go to a next location. So operation 10, any global parameters that you want to basically play with, like maximum size of the mesh, minimum size of the elements, and so on, you will be able to change them. Anyways, let's go to a die, define it. And because die model is already there along with the die face, I can simply select it from the layer itself. I don't have to even select by window. I'll simply go ahead and select it and include that. Die got defined. When I come back, you are able to see blank and die now because two things are already defined. I have just rotating and showing it to you. Yeah. Now I can go next and select punch, define that. Now, barring die face, the punch is all complete area, middle one. So there is a selective things. That's the reason I'm basically going ahead and select by surface. I'll just select it by window. This may be a wrong selection because it is showing even other surfaces got selected, and I'm deselecting it again. There are multiple ways to select them very efficiently, but for now I'm just going ahead with this option that I generally use. Yeah, this is also not required. All right, this also comes in the flat area only. Okay, so this is my punch area, including. Because it converts from geometry to mesh model. mm, it takes some time when we come back from geometry to this. And if you rotate and see, you have a punch, blank, and die. Now, needless to say, binders is basically just a flat surface of the die face, right? So I can just quickly go and define them. Fine. Same orientation again, top, and I'm just selecting the outer surfaces, flat surfaces rather. So wherever this window touches it, basically is that. So that's the reason I'm selecting area which can help me touching more number of surfaces. Yeah, all right. Yeah. So this is my binder. So for operation 10, whatever is needed, if you look at the tree, everything turned black. So everything is selected for operation 1. But since it's a progressive, operation 20 and 30 is placed somewhere else, you can define stroke that you want. You can increase, decrease from here so that you can optimize the solving time. Now, within this, if you want just a 1D draw, I mean, you're not created that draw into the die face, okay? You can actually do over here itself, so that you don't have to modify the geometry. This is really good. So I'm just importing these curves. Um though it looks only lines, but then when you get into the shape of the draw beads, you are able to see whether a rectangular type of the beads or round type of the beads having different parameters, R1, R2, R3. So though it's a single curve, you can actually segmentize it. These are the all parameters that is there, R1, R2, R3. So this particular segment, I can further divide them the way I want in particular area, because material flow you don't need same and all the location. So I'm just defining let's say this particular segment as one segment, In short, breaking that into segment, and you can define different strength in a different segments. Yeah. So, in, uh, in fact, though the your flat area looks very simple, because all the bits that you're defining in 1D form only. Okay. So all segment one, two, three, four, five, you're able to see. You can simply, um, modify the strength and forces in each beats in a segment. You know, Forming motions, you basically want to keep stroke of 800, velocity, things like that. And I'm sorry, this is the velocity curve that you want to define. So my operation one, including beads, 1D beads, is already done. So I can move on to operation 20 now. But since it's a progressive, my there is a shift in x direction of, let's say, 1600 is the shift in the stations. Obviously, practically, if it is different, also it shouldn't be a problem. We simply want to able to shift it over here so that it clears the area. That's it. Okay. And here I'm just adding trim lines which are already defined. Okay. Can you see this blank and a streamline basically has gone to a 1600 mm in X direction, next station. And let's say if it is done laser cut, you can just see the parameters, what is the capped minimum and tolerance that it can provide you. Likewise, we can go to operation 30. Um, you can define 3200 so that it goes further um to the next, right? 3200. You can even change the orientation also of the next operation, depend on your requirement. And here you want to basically define padding and cam as well, because that is needed in the third operation. So you are able to add a lot of other things here, including padding. So in the geometry, we already have one layer called pad. If you choose that, it should automatically shift once you include it. It should shift to the third location. And you can as well define cam. We also have cam geometry available with us. Obviously, it needs more treatment, what is the direction in which the cam is going to operate. So there is an angle. Then you can define the direction along v axis. There is an angle in which the cam is going to operate. You can adjust the stroke here also. When should cam process? So there is a sequence to it, whether it is after Defect. Yeah. So you can see all three operations sorry, all three actions in the under this operation, padding, cam, and all those. Okay, if you go and preview, I'm sorry, I think one operation is still pending. So let me just go back. So 10 farming, 20 trimming, 30 flanging, um, and if you just see how it is basically going to solve it, all the three stages. Yeah, you can see even cam movement right at the third stage. So this is how you will be able to preview before submitting your solution to a solver. I mean, here you have a choice to submit it to LSDyna or SIGFARM. Okay, line trimline and development. I can probably leave this because this is just to optimize the trimlines. Uh, this is another example of that. There is a tube bending and a forming for which you will be able to design the tooling for tube bending and validate how forming limit diagram is actually happening. So it's not alone bending, it has a lot of other function other operations also, like flattening the tube and so on and so forth. Then the most important thing, the die that you have designed, whether it is going to sustain the loads that are actually that it is subjected to or not. So carrying out structural analysis of die punch binder by applying forces extracted from farming simulation. So you're actually extracting the forces from farming, whatever realistic forces it has. You're applying those forces automatically on the model in Dynaform, and you can submit that in LSDyna as a solver. Once it is solved in LSDyna, you can take the results back to Dynaform and post-process in Dynaform environment and see different results that are actually issued. Okay, this is farming simulation results. Obviously, without farming simulation, you will not be able to directly go on die structure analysis because farming simulation provides you loads. And also, you will extract loads after you finalize the farming. I mean, not that, any rough stage you can start taking the loads and use it for die structure analysis. It is just, it will be useless exercise, isn't it? So you finalize the farming, whether appropriate thinning and all those things are happening, everything is acceptable. Then at that stage, that particular iteration, you can extract forces and start doing die structure analysis. So just typical examples, typical results that we basically see, deflection in X direction, deflection in Y direction. The die structure in die is most critical is because die will have a lesser space to accommodate, maybe if you want more thickness or something. So generally, general observation is, die will have a maximum stresses and a deformation as well. Uh, but obviously, um, the other side, if you look at from lower side, you will have ribbing structure. So what that ribbing structure should be, so that it supports the complete die well for a given loading conditions. All those you can, so maximum principal stresses that are coming in the die, whether they are going to be acceptable or not. Then punch, as I said, punch will have a lot of space actually to put material. So most of the time, punch will not have much of a criticality when it comes to structural analysis. But however, it will definitely help you saving material if at all you are using a lot of material in the structure by putting appropriate rib patterns and taking out material which is not required at some places. Uh, That's it from my side. I hope I have uh, I've overshooted for a couple of minutes. I'm sorry for that, but then hopefully I've just um, covered what I wanted to communicate today. We can have few more things, added and auxiliary functionalities to sheet metal forming simulation in upcoming webinars. You can keep in touch with us. And if you have any questions, please, you can put your questions in uh, chat or you can directly ask.